Okay, thank you. To start, I think we should thank the organizers. I haven't been here the whole time, but it seems like a really wonderful summer school. So thank you, Pierre and Erwan. Okay, the goal today is to finally get to the proof of Mirzakhani's conjugacy from earthquake flow to Teichmuller unipotent flow, the action of 1T01. And this builds a bridge between flat geometry, which is the Teichmuller unipotent flow, and hyperbolic geometry, which is the earthquake flow. And that bridge began when we saw that there was an isomorphism between measured foliations and measured laminations. And that isomorphism tightens the lines of the measured foliation to geodesics. It continued when we saw that the bundle of non-zero quadratic differentials over Teichmuller space was isomorphic to MF cross MF minus a certain fat diagonal via the map that sent a quadratic differential to its horizontal and vertical measured foliations. Okay, and this thing that I've referred to as the flat diagonal is the set of measured foliations that don't jointly fill. And if they don't jointly fill, that means precisely that there's some other measured foliation with zero intersection number with both of them. And then we introduced the star of the show last time, which is this map F lambda, which requires that lambda be a maximal lamination. So for a fixed maximal lamination, we get a map from Teichmuller space to the set of measured foliations transverse to lambda. So that, again, is just the set of things transverse to lambda can be interpreted as the measured foliations mu, so that lambda and mu are not in delta. So in other words, you can form a quadratic differential out of lambda and mu. And to remind you, this F lambda x is called the Horace cyclic foliation. It's a transverse measured foliation. And it was defined on each triangle like this, just by foliating by Horace spheres until Horace cycles until the Horace cycles met in the middle. And then if you'd like, you can pinch this down without affecting the foliation on the boundary so that it has a singularity. So if I wanted, I could sort of erase the middle and redraw it like this. Okay, and the key property, and this was really the key property, well, one is that it's sort of a canonically defined foliation, and another is that the transverse measure is just given by hyperbolic length along lambda. So if I take an arc of a leaf of lambda, then its transverse measure is just its hyperbolic length. Okay, so somehow this transverse measure was recording the data of how all of the complementary triangles in lambda fit together. And that was seen in the fact that this is a homeomorphism. Okay, and part of our discussion of this homeomorphism was the concept of shear. So I'll draw this picture in the universal cover. So I could take, so let's see, draw a better picture. Two triangles, T1 and T2 in the universal cover. And recall that each edge has a center point. And the center point is obtained by looking at the point where the orthogeodesic hits the third vertex. And equivalently, that's this point here. That's where the singular leaf intersects the boundary. So I have a center of each triangle. And we said, OK, well, suppose that there's a leaf of this Horace cyclic foliation from this triangle to this triangle. Okay, and that's not actually true of every pair of triangles, but for every pair of triangles, there's some finite sequence going between them, so each can be obtained from the next by following a leaf. But let me just sort of mostly focus attention on pairs of triangles where you can follow a leaf from one and get to the other. So I follow this leaf, which sort of consists of infinitely many bits of Horace cycle, because it crosses infinitely many of these triangles. And I get to a point here. And then what I do is I look, how far do I have to go from that point to the center point? So this length is the shear from T1 to T2. Okay, and it's a signed number because this point could be over here if I slid this way over here. We're going to start today with what I'll call the fundamental lemma on earthquakes. This is not standard terminology, but I'll call it the fundamental lemma to reflect my true belief that it is somehow fundamentally how you should think of earthquakes. It's not just a lemma. It's not just proven to prove this theorem. Somehow, you can almost incorporate this into part of your definition of what earthquakes do. OK, so here I'm going to have this. I'm going to call this arc A. OK, so I want to think about what happens to the shear. So I have the shear from T1 to T2. And here this is the hyperbolic plane, which is the universal cover of X. And now I want to think about what happens when I earthquake in lambda. So I'm going to earthquake for time t in lambda of X. And I could do that in the universal cover. So these two triangles are two triangles of lambda, or lambda tilde, and then many others. And so I could just do the earthquake upstairs if I want. I don't have to do it downstairs, if that clarifies anything. And I want to understand how that relates to the shear before doing the earthquake. Okay, and they're not equal. Right? You can imagine if I'm doing a right earthquake, which sort of shifts everything to the right, somehow the shear should be getting bigger. It gets bigger by a simple amount. And it's by this transverse lambda measure of this arc. OK. So where lambda A is the transverse lambda measure of an arc from T1 to T2. Yep?
So it's possible that before the earthquake, the shear is well defined. After the earthquake, the shear is not well defined.
Absolutely, it's possible. Okay. But that shouldn't worry you for two reasons. One is it's actually quite easy to define shear for two general triangles. You just form this path of triangles where each can be reached from the next by a leaf of the foliation, and then you just add up the shears. So you extend by linearly.
Singularity or something like that.
There's nothing to worry about with that. You just sort of can go from one triangle to the next and add up the shears. Second, really all I'm going to use is the derivative version of this. So what I'm going to use is I'm going to use the d dt of this is equal to lambda A. And that will actually be sufficient for our purposes. And if you do just a very small amount of earthquake, then T2 will still be accessible via T1 by following a leaf of the foliation. So in other words, the change in shear is equal to the transverse measure. That's how you should remember this. And this idea has been around since earthquakes were defined. And indeed, if you look at Kirchhoff's paper, which might be the first paper, one of the first papers where earthquakes were discussed in detail, he sort of says that this is part of the idea of the definition of an earthquake. Okay, so somehow the amount of shifting corresponds to the measure. Okay, so let me give the proof. So first of all, just take t equals 1. I mean, the only reason I put t there is to sort of make it seem more dynamical. But t lambda is just an arbitrary, like that's just the foliation. You're just scaling the foliation. So replace lambda with t lambda. OK. So I want to get back to sort of our original definition of earthquakes. OK, so I think I'm doing an earthquake. Maybe I'll just define my earthquake to fix t1. And then I'm trying to figure out what happens to t2. Okay, so this is very similar to our original discussion where I said, oh, I'm going to define my earthquake to fix one unit tangent vector. And I'm trying to figure out what happens to another unit tangent vector. OK, and there are infinitely many leaves of lambda that separate t1 from t2. Okay, and those are really what matters if I'm trying to figure out what happens. So let me redraw the picture. Make it look at least vaguely similar. Okay, so I have this. So infinitely many leaves of lambda separate them. But I can approximate the earthquake with a finite set of leaves. Okay? And I'm going to approximate it by a finite subset of the leaves. Okay, so infinitely many leaves of lambda tilde separate t1 and t2. And I'm going to approximate with a finite subset of these leaves. Okay, and I really want to emphasize that I'm using a subset of the leaves, because that's what's going to clarify here. I could approximate with any finite set of geodesics with appropriate weights on them so that that approximated the measured lamination. But I don't want to use just any geodesics that are close to these. I want to use an actual subset. Okay? And so to start with, maybe I'll just think about what happens if I did 1. Okay, so I pick one leaf and I earthquake along it. So that's a pretty bad approximation, but let's start the discussion there. So I have my 2 triangles. And I just pick one. So this is one leaf of lambda. Okay, and I want to think about what happens when I earthquake in that leaf and how it changes the shear. Okay, and then after doing one leaf, I'll do a finite set of leaves with different masses, and then they'll take a limit to get actually earthquaking in lambda. Okay, so what happens when you earthquake in this? So I can just define the earthquake to fix this half, and it shifts this half by an isometry. So earthquake, so one leaf, call it gamma. Earthquake in gamma shifts half of the hyperbolic plane, namely the half above gamma, by translation in gamma. By translation in gamma. Okay. And so when I do this, I'm going to sort of push the whole foliation, the whole measured lamination. And the measured lamination is going to be taken onto itself. Okay, so this maps lambda to the version of lambda on the earthquake surface. Okay, so right, all of the triangles up here get shifted by a certain amount. I'm going to just apply it to the whole, to all of lambda. And so what am I doing? So that maps lambda to itself. So it's going to map the Horace cyclic foliation to itself on this half space. So here I had this arc like this. And then after I do this translation, So I'm going to say translate that over here. Well, that will, so I probably, my picture won't be accurate anymore. But that will map this triangle onto this one, just via this translation isometry. Yeah?
Sorry, I'm somewhat confused about this. What is the lambda measure?
Oh, the purpose of a measured lamination is to give a transverse, like a measure to transverse arcs.
Yeah, but
So just by definition, a transverse measure gives you a number for any transverse arc.
so we don't have any measure on lambda, right? Lambda has no measure.
No, lambda here has a measure. So here lambda is a maximal measured lamination.
I just said that it doesn't need to have a measure.
You don't need a measure to define f lambda, but you do need a measure to define an earthquake.
Oh, okay, thank you.
So for this to make sense, the shear is defined in terms of f lambda, so I need lambda to be maximal. Earthquake uses a measure, so I need lambda to have a measure.
Yeah, but I remember last time you mentioned that A is just some segment along the foliation. So
Yes.
it is not transverse to the foliation. Yeah, because A is...
A is transverse to lambda. A is a leaf of f lambda mu.
lambda is a lamination.
Yeah, so A is a leaf of f lambda mu. Okay, that's the definition of shear. You follow the transverse foliation from one triangle to the other, starting at the center point, and you see how far you are away from the center point at the new triangle, at the second triangle. Yeah?
Why are we allowed to take the earthquake specifically with some leaf that crosses the cover?
So I can approximate the earthquake here with an earthquake on some finite subset of the leaves with appropriate masses. And here I'm just saying, suppose I did a very poor approximation and I just picked one leaf. I'm not saying that's a good approximation. I just want to start the discussion with an easy picture. Okay, so one, it's sort of meaningless because it's not a good approximation. But from one, we'll extrapolate to finitely many, and finitely many is a good approximation.
But in this picture, we have only T1 and T2. Where is T?
What? There's no T. There's T1 and T2.
In the formula, you have T, T2, and T1, T2.
There's little t, which is the amount of time we're earthquaking in.
No.
There's a comma missing. There's a comma missing. It's T1, comma T2.
Oh yeah, it's shear T1 comma T2. It's the shear between the two triangles. Okay, so I apply this earthquake and it maps this triangle onto this other triangle. And on this half plane, it maps the Horace cyclic. So I'm hitting the whole lamination on that half plane with that earthquake. So it just shifts everything by that translation. And so in particular, it hits this arc, this leaf of the foliation to a leaf that goes like this. And this is T. Okay, so if I do this, and sort of the relative position of this point to the center of the triangle is exactly the same, because I've shifted by an isometry, this translation. So in this case, shear, so earthquake in gamma for whatever amount of time, so whatever amount of mass I put on it. So I'll write m gamma because you put some mass on that, approximating the mass of the total measure. T1, T2, you have an exact equality on the nose, not an approximation. This is the original shear plus T. Okay, because you've just shifted by exactly T. So now you get from one triangle to the other by going up, and then going over by T, and then going up, and then going however much you needed to go to get to the center point. Into the amount you have to go along lambda to get from one center point to the other. Okay, so this is an exact formula. And the same formula holds for finitely many leaves of the lamination. So if gamma 1 through gamma k are leaves of lambda tilde separating the two triangles, then I could shear, and I could do the earthquake in some mi gamma I. So mi is the mass I'm giving to gamma I, T1, T2. And exactly the same logic says that I'll get the original shear plus the sum of the masses. OK, now I can pick a finite linear combination of the geodesics in between to arbitrarily well approximate the lamination. And when we defined earthquakes, we'd said that the earthquake is the limit of the earthquakes in approximations. OK, so taking a limit as some mi gamma I converge to lambda tilde, and this is just, we only care about between T1 and T2, we get the result. OK, so the idea is we just approximate the earthquake with earthquake in finitely many geodesics. And if they're geodesics that are actually in lambda, we can precisely understand everything. OK, it would actually be a bit of a disaster if we tried to approximate it with geodesics not in lambda, in that then it would be, I wouldn't know how to exactly compute how the shear changes. OK, so it's sort of important we're approximating in the universal cover rather than on the surface. OK, so anyways, you can forget the proof now. Just remember this fundamental lemma, which is you should incorporate into your sort of core idea into what earthquakes do. The amount of shearing, the change in shearing for an earthquake corresponds to the transverse measure. OK. And maybe right away, let me compare that to unipotent flow. So take a saddle connection with period xy. And I want you to think of x as the shear of this saddle connection, because it's sort of how much you had to move in the horizontal direction. And if you think of lambda as the horizontal direction, the shear is how much you have to move in the horizontal direction. And you should think of each of these as corresponding to a triangle. Because indeed, if these are simple singularities, not on saddle connections, then when you tighten, they give triangles in the associated lamination.
What is that vector we, I'm sorry, what is
Oh, this is a saddle connection.
what is the vector xy?
And this is its holonomy. Okay, and I just sort of, the basics of unipotent flow is this equation. Okay, so let's call these points P1, P2. So Pi corresponds to the triangle, right? Because each singularity becomes a triangle in the associated lamination. And X corresponds to the shear. OK, and maybe we'll just call this saddle connection A. So A corresponds to A. And then I do Horace cycle flow, and the shear changes by T times Y. But what's Y? So here's the horizontal measured foliation. And so, OK, let me also say horizontal foliation corresponds to lambda.
When you say unipotent flow and Horace cycle flow, are those the same thing?
Yeah, Teichmuller unipotent flow, Teichmuller Horace cycle flow.
Okay. And, okay, but just another cultural difference here.
Partially it's to keep it apart from the Horace cyclic foliation. Partly it's...
You're not suggesting that everybody switch over to the unipotent flow.
No, although there are those who do very strongly suggest that. But I prefer not to enter that discussion. Let's say I'm doing it to separate it. So here, this I'm just calling the unipotent flow. OK, so this y is the transverse measure of A with respect to the horizontal foliation, which is maybe not how you're used to thinking about it, but that's what it is. So then you see, how does the shear change if x is the shear? Well, it changes according to the transverse measure of A. OK, so this was a bit vague, but the point is this fundamental lemma is the analog of this equality. So I would call this the fundamental lemma of Horace, of Teichmuller unipotent flow, except it's not a lemma, it's a it's basically the definition. But this is, you're supposed to compare these two things. And the proof will consist of comparing those two things. But now let's get to the proof. So now I want to define Mirzakhani's semiconjugacy. So I actually have to tell you the map. So the map is not defined everywhere. It's defined on a full measure set. Okay, it's a measurable conjugacy, so I only need to define it on a full measure set. And the full measure set I'll call, very uncreatively, I'll call it QD0. And it's the locus of quadratic differentials so that they have only simple zeros and no horizontal saddle connections. Okay, so this is the full measure subset of the locus of quadratic differentials. And here's where I'm going to define the conjugacy. Yeah, so somebody just said the word maximal. So the idea is this is supposed to correspond. So remark, this condition is equivalent to the horizontal foliation being, the horizontal lamination being maximal. Right, each simple zero that's not on a saddle connection gives a triangle, an ideal triangle for the associated geodesic lamination. If you have simple zeros, this is just a check, one of many ways you can prove this correspondence. If you have simple zeros, you have 4g minus 4 zeros, so you get 4g minus 4 triangles. So the area of the triangles is 4g minus 4 times pi. That's the whole area. So you've covered the whole surface. That's all of the complementary regions.
If you had one, say, horizontal saddle connection, you'd have a quadrilateral?
You'd have a quadrilateral. And similarly, if you had 1, 0 of order 2, you'd have a quadrilateral. OK, so I'm looking at the set of quadratic differentials whose horizontal lamination is maximal. OK, and so I should define ML0 to be the maximal measured laminations. And I'm going to define, so Mirzakhani's conjugacy is called F, and so at first I said it was a measurable map from ML cross Teichmuller space to quadratic differentials. Okay?
Sorry, which maximal lamination is ML0?
Oh, it's the set of all maximal laminations. So this is a full measure subset of ML. OK. So you can do Mirzakhani's map as a measurable map here, or you can define it as an actual map from ML0 across Teichmuller space to QD0. And I'm going to view this. These are both full measure subsets, so I'm going to provide a bijection between the two full measure subsets. And this bijection will conjugate Horace cycle flow to earthquake flow. And this bijection, it can't be extended to a continuous bijection from ML0 to Q, from ML to Q Okay, so you have to take out a set, a bad set. So
Are you claiming it's continuous on this set?
I think it's continuous on this set, but I haven't checked the details. I think I could describe to you in detail exactly the failure of continuity of the map, the failure of its, exactly to what extent it fails to have a continuous extension. Okay, and this F will be really, really easy to define. We've done all the work already, and it won't be so hard to show that it's a conjugacy either. Okay, so the map, so I'll write it here. So F takes in a maximal measured lamination and a point in Teichmuller space. And from this, I need to define a quadratic differential. So a quadratic differential is defined by two measured foliations that are transverse, or two measured laminations that are transverse. And now you can, I bet some of you can already guess what I'm going to do. I already have one, it's lambda. Okay, and I already sort of hinted that lambda is supposed to correspond to the horizontal foliation. So lambda is going to be the horizontal foliation. And what should I use as the vertical foliation? I should use the Horace cyclic foliation, F lambda of x. Okay, that's the only transverse foliation I have around.
Plus you wrote it in such a way that there's no other letters that fit into this one.
Yeah, plus I wrote it leaving exactly that amount of space. Yeah.
What is that Q?
Oh, so by Q, I mean, if Q is the map from MF. So Q goes from MF cross MF minus delta to QD. So it's the map which, given two transverse foliations, forms the associated quadratic differential. Okay, so I just take the quadratic differential defined by the two foliations lambda and the Horace cyclic foliation. That's the map. Okay, so that's why I said the Horace cyclic foliation F lambda, that's the star of the show, because that's really all the work is, you have to define that and understand it. Okay, so that's the map. We already understand how shear changes, and we see some similarity to this. And so now, okay. So F is a bijection, follows from F lambda, which goes from Teichmuller space to M F lambda, is a homeo. So it follows from this statement. Right, MF lambda is everything transverse to lambda. So I've essentially checked it on slices. We already know that this is a bijection. Okay, so all I need to show, is that, so need to show F sends a earthquake path to a 1T01 orbit. So that's all I need to show. To prove Mirzakhani's theorem that F is a conjugacy, or that F conjugates earthquake flow to Horace cycle flow. So I already know that F is a bijection. I just need to show that it maps earthquake to Horace cycle.
So you wrote it in such a way, I mean, are you proving an orbit equivalence result, or are you actually?
No, I'm going to prove it in a parametrized sense. So I'm going to prove it's a conjugacy.
So you need to show a little bit more than what you wrote.
That's what I meant, though. Okay, so let me write down a lemma that will, I'm not sure if this is completely required, but it'll clarify things, and I think we'll do a little bit of easy work on the quadratic differential side, and everything will seem a little easier. So for any quadratic differential, every isotopy class, or every path from one singularity to another can be isotoped rel endpoints to a sequence of paths like the following. So a sequence of paths that go from a singularity, travel horizontally for a while, and then travel vertically for a while and hit another singularity. Okay, so if you have any path joining one singularity to another, you could realize it. So I have a path from one singularity to another, and I can isotope it to look like this, maybe. Something like that. Okay, so there's a proof in the notes. It's really easy. You can try to do it for fun if you want. It suffices to do it for saddle connections, because every path can be isotoped to a sequence of saddle connections.
Your claim is monotonous also, or can you go up and down?
No, you can go up and down. Yeah, it's okay. You can go up and down. Okay, so I'm going to erase the definition of the map, but don't forget, the semi-conjugacy, the thing we're trying to show is a semi-conjugacy, sends a lamination and a point in Teichmuller space to the quadratic differential defined by the lamination and the Horace cyclic foliation. So lambda becomes the horizontal foliation, and the Horace cyclic foliation becomes the vertical foliation of the quadratic differential. So I'm going to write a corollary of this. So suppose QT is a path of quadratic, so it's a path in QD. It's a path of quadratic differentials. And suppose for every t0 and every path gamma on qt0 as above. So by as above, I mean like this. It's a path that starts at a singularity, goes horizontally, makes a right turn, goes vertically, and arrives at another singularity. And we already have in mind from this lemma that somehow is enough to capture all paths. As above, the holonomy, well, let me just write it. If the holonomy on qt of gamma is xt plus I yt, well, I'll just set that as notation. Then, if the following two things are true, so if the derivative in time of xt is yt, and I just need this at t equals t naught, and the derivative of yt is 0, then qt equals 1t01 of q0. Okay, so let's just sort of decode this one step at a time. The first version of this lemma is just suppose you have a path of quadratic differentials, and all the periods change according to the matrix 1, T0, 1, then that path has to be an orbit of Teichmuller unipotent flow. Okay, that's just the definition of Teichmuller unipotent flow, right? Period coordinates are coordinates. They capture everything. If your coordinates are changing according to 1, T0, 1, then by definition, your path is an orbit of 1, T0, 1. Okay, and the next version of this lemma is like, okay, well, it suffices to check a derivative at every point. Right? You just need to show, so let's just never forget this sort of fundamental thing. 1, T0, 1, xy is x plus ty y. So the derivative of y shouldn't change because it's constant, and the derivative of x should change according to y.
That's a question I should have asked before. So what exactly do you mean by qt is 1, T0, 1, q0? I mean, how do you think formally about this?
So this is just the Teichmuller unipotent flow defined by John and Barak. So one way to do it is present this using as a polygon or a collection of polygons, and then hit those polygons by 1, T0, 1.
That's translation surfaces.
That works for quadratic differentials too. Yeah, equally well.
But these are quadratic differentials on maybe different Riemann surfaces, right? I mean, the quadratic differential also gives me the Riemann surface.
Yep. It's exactly the same for quadratic differentials as it is for abelian differentials. John?
Yeah, so we described an SL2R action for translation surfaces. If you think about a PSL2R action, then that works for quadratic differentials.
Yeah. Still an SL2R action that just factors through PSL2R. Right, every quadratic differential can be represented as polygons with parallel edges identified, now via translations or translations and rotations. Some people call these half translation surfaces, and you just act linearly in the same way as you did for translation surfaces. Okay, or the other definition is you just follow in period coordinates and change the periods according to 1, T0, 1. Okay, so okay, are there any questions about this? You should think that this is obvious. I've sort of written it in a complicated form because this is the easy stuff, so we'll do the work on the easy side. But this is just saying, so, these paths gamma, their span and relative homology is everything. So you can get every path as a concatenation of these paths. So by the lemma, you get this for all paths, and then the proof just consists of, if you have a function, which is these periods. So first of all, consider the y coordinate. If you have a function with zero derivative, it's constant. Okay? And then if you have a function with constant derivative, it's linear. So that's the proof. Okay, so this is what I'm going to check. I'm going to take the earthquake path. I'm going to hit it with my conjugacy f. And then I'm going to check that this property holds. And as I said, I'm sort of doing it infinitesimally just to clarify. I'm not saying you couldn't do it in a non-infinitesimal way. To me, it's sort of clearer if you do it in an infinitesimal way. Okay. So we're now ready to do the proof. But before we do the proof, I want to sort of make a table showing the correspondence between things on a different side. Because really, most of the proof is getting used to the definitions and sort of starting to see they really look the same. Okay, the proof is not that technical. We've done most of the work. So maybe I'll put it, everything here is good. I'll erase this. I'll put this board back up in a second. I just want to write this sort of fundamental table of comparisons, what corresponds to what. Okay, so we want to show that earthquake flow corresponds to Horace cycle flow. Or I'm calling it unipotent flow, I guess. Teichmuller unipotent flow. Well, 1, T0, 1, acting on the bundle of quadratic differentials. Okay. So in our dictionary, so first of all, lambda is going to correspond to the horizontal foliation of the quadratic differential. F lambda x is going to correspond to the vertical foliation. This is h of q, and that's v of q. It's an incomplete x. Okay, so then the pair lambda x corresponds to the quadratic differential q, and this quadratic differential is lambda f lambda of x. So that's the map, that's the conjugacy. Okay, so a triangle in x minus lambda. So this is one of these complementary triangles. That corresponds to a singularity of q, a cone point of angle 3 pi. So we're just doing the minimal singularities. And the shear corresponds to the x component of a holonomy, or a period. And the fundamental lemma, as I said, that corresponds to the equation 1t01 xy equals x plus ty y. Okay, so we'll make all of this precise momentarily, but I just wanted that up there on the board so you can continue to refer back to it. So now let's do the proof of main theorem, i.e. that f conjugates earthquake flow to unipotent flow. Okay, so we already know f is a bijection. We just need to show the conjugacy. So exactly what we need to show is we need to show that q of lambda, f lambda of earthquake flow, lambda of x is a 1t01 orbit. People want me to say in a parametrized way. So that if this is 1t of what you get at time 0. Okay, so this is exactly what we need to show. So we need to show that this is parameterized Horace cycle flow path. And what we're going to use is this corollary. Okay, so we need to understand how certain holonomies, or certain periods and holonomies is synonyms, we need to understand how certain periods change. Okay, and I'm going to show you that this is an exact consequence of the fundamental lemma of earthquakes. That's exactly what it is and nothing else. Let me just rewrite this the way Barack would want me to, so I have more room. Okay. So we'll apply the corollary, and without loss of generality, we'll take T0 to be 0. OK. So I need to draw the most important picture. I don't know where to put it. I'm trying to fit everything here. So you should have this in mind. To draw sort of a hybrid picture, which is a little bit misleading, but also a little bit helpful. So I have two triangles in the lamination. OK? And I have a bunch of leaves of lambda in between. And the misleading thing is I'm going to draw them as straight lines, when really they're hyperbolic geodesics. But we're sort of starting to think in the flat picture at the same time. It's sort of a hybrid picture. It's a schematic picture, if you'd like. OK? And the triangles that I understand best are the ones where I can get from one midpoint to another point by going along a leaf of the foliation and then going along there. Okay. This is a leaf of f lambda, so that's a vertical path, right? Because f lambda is the vertical foliation. And this is a leaf of the horizontal foliation. Okay? So this path exactly corresponds to one of the periods we can actually understand. Okay, so this whole triangle gets collapsed to a singularity. This whole triangle gets collapsed to a singularity. Right, so consider a path gamma in h equals x tilde from, as shown. So gamma course gives a path on q lambda f lambda x that follows the vertical foliation, which is f lambda of x, and then lambda, well, the horizontal foliation of q, which is lambda. So this is one of the good periods that are, it suffices to consider these. Okay, so the corollary says it suffices to consider some periods. Periods are exactly the ones that are easiest to understand. Okay, and that's why I set it up this way. I think you could get around this by just setting up sufficiently general definitions, but for me it's simpler just to think about these paths. Okay, so say the holonomy of gamma on this, let's call it qt. This is our path qt that we want to show as a unipotent orbit. On qt is x plus xt plus iyt. Okay. So yt, the transverse lambda tilde measure of this path over there, which you can view as the arc A, and this is constant. Okay, because I'm not changing the horizontal foliation. I'm not changing lambda. That's the easy part, right? The map that I'm doing evidently does not change the horizontal foliation. That is constant as I do earthquake flow. Okay, so now all I need to do is think about xt. So xt, what xt is, it's exactly the shear, right? Because as I go along the vertical foliation, I don't pick up any x change. So in here, I pick up pure x change. So xt is exactly the shear on earthquake flow t lambda of x from t1 to t2. And this is by the fundamental lemma, this is the shear on x of T1, T2, plus T times y, because y is the transverse measure. Right? Y is the transverse measure. Okay? And this is exactly what you want. Oh, this is supposed to be, yeah, plus. Right? The change in the shear is the transverse measure. Okay? So you can already sort of see you don't really need to phrase everything as a derivative. I just phrase it as a derivative to make it clear that we don't have to worry about one triangle becoming non-accessible, and we also don't have to worry about chaining together these triangles. It just suffices to do this. You can also just set up different definitions where you define shear by chaining triangles together and then not do derivatives. Okay, anyways, that's the whole proof. Okay. The periods change exactly as the periods change for Teichmuller unipotent flow. Right? So that means the earthquake path maps to an orbit of Teichmuller unipotent flow. Okay, so any questions? Yes?
So what meaning of holonomy of connection?
Holonomy is just you like integrate. So locally, so maybe put it this way: the saddle connection lies in the plane. If you write the surface in terms of polygons in the plane. So the saddle connection can be thought of as a line in the plane. So that's a vector. That vector has displacement x comma y. So x plus iy is the holonomy. Or I also call the period. Other questions?
Can you just formulate in what sense these are coordinates?
So the edges of the polygons are all holonomies. And if you have all those holonomies, you know the polygon locally.
So I may have more than I need, but...
You may have more than you need, then you can store some away. Okay? If you want to be abstract about it, the local coordinates come from the -1 eigenspace in the double cover, blah, blah, blah. Okay. So just to make a few quick remarks, and I won't write because I'm basically out of time. So I have this conjugacy, and I have an invariant measure for Horace cycle flow, namely Masur-Veech measure. Okay, so that must mean that there's an invariant measure for earthquake flow. Okay, and that invariant measure comes from the Weil-Petersson metric. Okay, the Weil-Petersson measure in a straightforward way. So there's a relationship between Weil-Petersson volumes and Masur-Veech or Thurston volumes. And when you carry this through, you get exactly the formula that Anton referenced yesterday, that the Masur-Veech volume of the principal stratum of quadratic differentials is the integral over mg with respect to Weil-Petersson measure of the Thurston volume of the unit ball, in MF. And so that you prove that, you don't need to know it's a conjugacy, you prove that knowing that F lambda maps, so it's a theorem of Bonahan and Sozin that F lambda maps the Weil-Petersson volume to the Thurston volume. And actually it maps the Weil-Petersson symplectic form to the Thurston symplectic form. So it's even better. And I'll just end with one other comment. I think there are some interesting things to be done. So this stuff is connected to a lot of things. So for example, it's connected to Thurston's asymmetric metric on Teichmuller space, where geodesics are described using stretch paths. Stretch paths are obtained simply by multiplying F lambda by a constant. Okay, so the map F lambda is a coordinate on Teichmuller space, and if you just scale it, then you get these things called stretch paths. And Mariam's semi-conjugacy also conjugates stretch paths to the action of 0, 0, 0 e to the t. So basically Teichmuller geodesic flow, except you have to be preserving the horizontal foliation. I'll also comment that you can't make this f continuous, but I think you can understand the extent to which it's not continuous. I don't think that's been done, but I think it corresponds to the understanding how you can complete a lamination to a maximal lamination. Because the point is you can't define f lambda if lambda is not maximal, but there may be many definitions as you fill in. And then I'll also comment that I think there should be a conjugacy between Horace cycle flow on each stratum and some locus, some interesting locus in ML cross Teichmuller space. And if you want, you can come ask me about that. So I think there are many things left to be done with Mariam's ideas. And I have much more details and many related things in the notes online. So I encourage you to ask questions to me or refer to those notes in the future if you're interested. OK, thanks.